Welcome to video 19 in our series on tensor calculus. For 18 videos now, we've had a lot to say about tensors, and we've shown several examples of how to work with them, but we've never really defined them. Well, we have now covered enough basic information that I think you can finally appreciate a formal definition. Here we have the generalized form we use to represent the scalar components of a tensor. Now, I'll remind you that a tensor is a geometric object that exists quite independent of a coordinate system. And when we speak of it in that context, we represent it simply with a capital letter, usually in very bold font. However, when we do introduce a coordinate system, we can decompose it into its individual scalar components. You're familiar with this concept where a vector is concerned. A vector is a geometric object that exists independent of a coordinate system, but when we introduce a coordinate system, we can decompose it into individual scalar components like this. So we can do the same thing in general for any tensor using the form represented here. So let's talk about the form a minute. It's a capital letter with any number of indexes, 0 to any number along the top, and any number 0 to any number along the bottom. Here we've represented it as having A indexes on the top and B indexes on the bottom. And as you might have already guessed from previous discussions, the indexes on the top correspond to contravariant properties, and the indexes on the bottom correspond to covariant properties. All right, we speak of the rank of a tensor, which is normally represented by the letter R, which will be equal to the sum of A and B, being the number of indexes along the top plus the indexes on the bottom. So the total number of indexes used will equal the rank of the tensor. And because we can have any number from 0 to any number we choose in either place, then the rank of the tensor could be 0 or anything higher than 0 as long as it's an integer. For example, we would speak of this Tij as a second-rank tensor that is twice covariant. We would say that this is a second-rank tensor that is twice contravariant. We would say that this tensor is a third-rank tensor that is twice contravariant and once covariant. And it's common to speak of a tensor like this that has indexes both on the top and the bottom as a mixed tensor. Now we can also have a tensor of rank 0, which is one that has no indexes. It would be represented by the letter but not in bold font. This is simply a scalar function. Now one of the rules we have to adhere to is this, that all of the indexes on either the top or bottom have to be unique. No upper index can duplicate any other upper index at any time. So this would be an invalid representation. We can't have the letter I used twice on the top. The same is true on the bottom. We can't have the same letter represented two times anywhere in the stack of indices in the bottom. Now, it is possible to construct tensors in which a letter on the top, one or more of them, is duplicated on the bottom. This would be a valid form. We see J used on the top and bottom, and this kind of construction is known as a contraction. And we'll talk about that in a couple of videos, but we'll assume for the remainder of this video that all the indexes are unique both on the top and bottom and throughout the entire expression. So you can see that it's pretty simple and straightforward to represent the components of a tensor with this form. However, it's important to understand that just representing something in this form does not make it a tensor. We're going to run into a number of objects that have the correct form here but turn out not to be tensors. So what we have to say is this: a tensor is an object that can be decomposed and be represented in this form and satisfies the condition we're going to talk about next. Take a look at this expression. What I've done is to take our generalized form for tensor components and I've multiplied by a set of arbitrary vectors. Now, this is a set of arbitrary vectors, all of which have covariant components. And the vectors I've chosen match up one for the indexes along the top. So since I have A indexes on the top, I have A arbitrary vectors of a covariant nature down here. Likewise, I have B indexes here. I paired each of those up with a set of arbitrary vectors like this. Okay, the result of that is that I have now paired every index with an index on one of these arbitrary vectors, and therefore all of the indexes are dummy indexes. There are no free indexes in this expression. And what that means is I have a single expression. It's not a set of expressions. It's only one that has a whole bunch of some terms on the right-hand side. Now the condition that we're talking about for a tensor is this. When I form an expression like this, it must create what we would refer to as a scalar function. Now it will produce a scalar value. There's no question about that, because all of these are dummy indexes and they just sum up to a value. The question is it a scalar function? And a scalar function is one that is the same value for all coordinate systems. So let's see where that takes us. The first thing I'm going to do here is I'm going to replace each of these arbitrary vectors with its corresponding transformation equation from primed to unprimed coordinates. So since this is a vector with a covariant index here, I've got to multiply by the Jacobian factor that has the free index down here on the bottom. So if you look at it closely, this expression is simply a covariant transformation of this one factor from the primed system to the unprimed system. Likewise, I've done the same thing here and the same thing for every one of these vectors throughout. Now on the second group of terms, these are contravariant vectors, so I've got to insert a contravariant transformation so that the free index is up here. And so this guy is represented by that. This one's the same as this. This one's the same as this. So I've done that for every one of our arbitrary vectors. Now the next step is simply to regroup them. I've taken each of the Jacobian factors here and put them in one expression. Each of these Jacobian factors here. And the factors for A go here and B here. I've just reorganized the factors. Now the next thing I'm going to do is to write down the expression, the original expression, as it would look in the unprimed system. So instead of being a function of z prime, it's a function of z, and none of the indexes have the prime symbol on it. Okay, so what we're saying is that if this is indeed a scalar function, then it must be the case that this expression has to be the same as that. In other words, we can equate this expression to this one. If it is a scalar function, these two expressions will be equal. Now, if that's true, when we set them equal to each other, you'll see that this whole group of terms cancel out with this, and this one cancels that one. And that leaves us with the following expression. So, here's the point. If this is a scalar function, then the transformation rules for our tensor components must be this. In order for this to be a scalar function, the tensor components in our generalized form must transform from the prime system to the unprimed system using this formula. Now, it's also possible to start our discussion with this expression and say that we require tensor components to transform this way in order for it to be a tensor. If this were the condition, we could work our way backwards to prove that this would be a scalar function. The point is that these two expressions are equivalent. If this is true, then this is true. If this is true, then this is true. The two are equivalent, and we can use them almost interchangeably. And just as a matter of interest, some texts use this as the definition for a tensor, some use this. You can use either as a matter of preference. As I say, they're equivalent. We'd say that this is the intrinsic definition of a tensor, this is the axiomatic definition, but they truly are one and the same thing. So to reiterate, we'd say that an object which is representable in our general form of the terms up here is a tensor if and only if those components transform between coordinate systems according to this rule. Now, what is the rule? Well, the rule is that for every one of the upper indexes, the contravariant indexes, we have to have a Jacobian factor for contravariant transformation in which the dummy index pairs with the one on the bottom here, and the one above is the free index matching this side of the equation. And every one of the lower indexes here have to pair up with dummy indexes here, and the free indexes along the bottom match here. So when we see a form like this, in order to know if it's a tensor, we either have to prove this or we have to prove this. Now, it's pretty easy to become overwhelmed by all of this abstract symbolism, so let's go take a look at how this applies to real examples. Let's start with a couple of trivial examples. Let's say we have a function that's a function of z that's a scalar function. Well, we already know that by definition a scalar function is the same value if we transform to the z prime system. So, according to our rule of transformation for a tensor, we have to see a transformation that includes a Jacobian factor for each of the indexes in the expression. But with a scalar function, there are no indexes, so there are no Jacobian factors. So this by itself meets the conditions that we talked about. It follows the correct pattern for the transformation of a tensor because it's a tensor of rank 0. Well, let's try this one. What about a vector component I that's a covariant component? Well, we know how that transforms because as a covariant object here, we have to transform to the prime system using a covariant transformation, and we know what that looks like. And this is also the correct form as per what we derived just a few moments ago. We have an expression with one index here, and so we have to have one Jacobian factor, and because this is a covariant index, we have to have a covariant Jacobian factor like this, and it all matches up. This is exactly right for our expression. Likewise, if we were dealing with a contravariant object, we know that this is the transformation needed there, and that matches our formula as well. We have to match every upper index with a contravariant transformation factor like this. Okay, so those are just trivial examples that demonstrate that they're completely consistent with what we derived before. So let's do something new this time. How would we go about validating our covariant metric tensor? We made the claim when we talked about this that it's a second rank tensor, twice covariant, and we just made that claim, but how do we prove it? Well, here's how you go about it. We would start with the definition, And you remember the definition of this is the dot product of zi with zj. Now, for each of these two factors, I'm going to replace each one with its transformation to the prime system. So I'm going to need a Jacobian factor like this. This needs to be prime. This would be an I prime. So that is the same as our first factor. We're going to dot that with the transformation for the j term here. So that's going to be a Jacobian factor of j prime times z j prime like this. So understand what I've done here. I have replaced this expression with its equivalent in prime terms. This one is replaced with a transformation in prime terms. Okay, now if we reorganize these things a little bit, you can see that this is equal to j I prime, j prime times z I prime dotted with z j prime like this. But you recognize, I hope, that this is just the expression for the covariant metric tensor in the prime system. So after doing all of that, we can say that zij then would be equal to this factor, which is z I prime j prime, that's just this expression, this dot product here, times the two Jacobian factors. This should have been a prime up here, and then j prime, j. And what do you notice? You notice that this is the form we talked about in our previous discussion. We have a tensor form that has two indexes on the bottom. So if it is a tensor, it has to transform by means of two Jacobian factors, one for each of the covariant indexes. And that's exactly what happens. So that proves, in this very simple analysis here, that the covariant metric tensor is in fact a tensor. And we are correct in choosing the lower indexes because they're covariant in nature. Okay, one more example here. Let me move down just a little bit. Made the claim in an earlier video that the Kronecker delta is actually a second-rank tensor. Let's see if we can prove it. Here we have the Kronecker delta in prime terms. If I were going to transform to the unprimed system, I would need a Jacobian factor for the contravariant index, and I'd need one for the covariant index like this. All right, where does that lead us? First of all, you'll notice that the Kronecker delta on this side can actually absorb the I prime index, so that this entire expression just becomes j prime. It is this index over this index that's left, and that's what gives us this term. Okay, so we'll bring the second term along, which is j prime j over here like this. And what do you notice now? Well, here we have a pair of Jacobian factors, but there is a dummy index here. And you'll remember that means that we can, these two combine together to form a Kronecker delta with these indexes. So those two together result in a Kronecker delta I, j, just like that. So now we've proven that the Kronecker delta is a second-rank tensor, once contravariant, once covariant, because in the unprimed system it transforms by means of a Jacobian factor for each of the indexes in the prime system. We have one here to match the contravariant index and one here to match the covariant index, and that's the form we need to prove that it's a tensor. All right, with those illustrations, I think we've reached a pretty good stopping point. So let's end this video with a short review. We said that the scalar components of a tensor would be represented by this form, in which we have any number of unique indexes on the top and any number of unique indexes on the bottom. We also said that the rank of the tensor R would be equal to the sum of the number of indexes on the top and the bottom. But we also said that just knowing we have the right form is not enough. We have to meet another condition in order to know if we really have a tensor. We can do that one of two ways. First of all, we can prove that this expression is a scalar function. And this expression is simply our expression for our tensor components multiplied by two sets of arbitrary vectors. The first set, the set of vectors that correspond to each of the upper indexes, like this. These are covariant vector components that pair up with the upper indexes. Then we have a set of contravariant vectors like this. Again, they're arbitrary, and they match up and pair up with the indexes like this. And if this expression turns out to be a scalar function, then we know we have a tensor. The other test, and probably one that's used more often than the first one, is to look at the transformation rule for a tensor. If our components transform as per this relationship, then we know we have a tensor. And the relationship is that for every upper index, there has to be a Jacobian factor paired up with it like this, such that the upper indexes of these Jacobian factors are the free indexes on the other side of the equation. Likewise, the lower indexes must pair with Jacobian factors like this, where the lower indexes of the Jacobian factors pair up with the free indexes on the other side. And if our components transform according to this rule, then we know that we have a valid tensor. Okay, with all of that, you now have a formal definition of a tensor. In the next video, we're going to begin a discussion of tensor algebra.